Yes, good morning, students.
Good morning, sir.
Morning.
Yeah, good morning. So today we'll discuss about this is spread spectrum communication system, okay, which is module 5. I will come back to module 4 after this. The purpose is it is scoring, okay. This module, few topics are there, not without much mathematical background, okay. Yeah. Uh, Yes, anybody is having any idea about this spread spectrum communication systems? It is spread spectrum. Is it possible to say what is the meaning of this? The word spread is there, then spectrum is there. What do you mean by spread? Yes, be fast, any one of you. Spread spectrum. No idea? At least you can interpret the meaning of the word, no? Spread spectrum. Means you are going to spread the spectrum, right? Say, let us think that the information signal, right, which is basically a low frequency signal, right? If I am going to spread that information over a wide bandwidth, then I can say the spectrum of the information signal has been spreaded, right, over the wider bandwidth, right? So that is what is happening here. The low frequency signal is basically a message signal, right, which is spreaded over the wide bandwidth and then transmitted over the channel. Okay, by doing so, we are able to achieve better security. Okay, better secure communication is possible with this type of technology. So that is why it has started with military applications. Okay, so this spread spectrum signals for digital communication originally developed and used in the military communications. Okay, so the characteristics of this spread spectrum signal is it provides resistance to jamming. Okay, and then it is also possible to hide the signal. Okay, by transmitting uh, at low power. Okay, I repeat once again, it is possible to hide the signal by transmitting it at low power. So by doing so, it becomes very difficult for an unintended listener to detect its presence in noise. Okay, that we call it as a low probability of intercept. Okay, so these are the two main characteristics of this spread spectrum signal. What I can say means this spread spectrum signal provides resistance to jamming. What we say is anti-jam protection. I hope you all know what is jamming. Yes, my dear students. Are you aware what is jamming? Yes, am I connected or not connected? I'm not getting any response. Hello?
Yes, sir.
Yeah, are you aware of jamming? Anybody in the class? Okay. So I understand keeping quiet is not aware of what is jamming. So let us try to find out, no? Google it. What is jamming? I would like to hear from your end. Okay. So maybe in another 2-3 minutes, I expect you people to say what is jamming. Yeah. So what I said is with the spectrum signal, we are able to hide the signal by transmitting it at low power. Okay. So with that, it becomes very difficult for an unintended listener to detect its presence in the noise. So with that, we are able to achieve reliable communication by using these spread spectrum signals, even in a variety of civilian applications. I said this started with or developed for military communications, and later on, because these spectrum signals can provide reliable communication, so with that it has been even used in the civilian applications also, like digital cellular communication, cordless telephones, inter-office wireless communications, and so on and so forth. Okay, so you find the use of spectrum in many civilian applications. Okay, so let us try to understand this. What is a spread spectrum signals? Okay, so basically, here in case of spread spectrum communication, the bandwidth of the modulated signal, okay, bandwidth of the modulated signal will be much greater than the message signal bandwidth. Say, for example, here I have taken the information signal or message signal having a bandwidth of B, okay, and this information signal has been spreaded, okay, by using a spreading code. Okay, that spreading code is known as the pseudo noise code, we say. Okay, PN sequence. You might have heard about PN sequence. Are you aware of this? What is PN sequence? Hello? Hello? I'm asking, are you aware of pseudo noise sequence? Yes, my dear students, please respond. No? If you are aware or if you are known about that, it is good. Otherwise, I can. Anyway, we are going to discuss about that, how to generate pseudo-noise sequence of particular length and all. But as of now, you might have studied. You have done an experiment also. I remember. But you are not able to say, yes, we are aware of that. You are not studied about random binary number generation. Hello? Hello?
Yes, sir.
You people have done the experiment, no? In the third semester, I think in the logic design lab. Have done or not? Random binary number generation. Yes, that was the last experiment, if I am correct. Yes or no? What is this, sir? Saying yes or no also taking so much of time. Yes, my dear students, please communicate, na? Are you aware of random binary number generation? Pseudo random number binary generation. Yes, why you people cannot unmute and say yes or no? Hello? Hello? Yes, you are all busy with what? Are you listening my talk? Yes, Aditi. Aditi. No, Aditi. Akshay.
Yes, sir.
Are you aware, man, how to generate pseudo-random numbers?
Yes. I don't remember it properly.
Okay, you don't remember it properly. Fine, at least. Okay, what about others? Nobody remembers, I think. That is why they're not talking. Okay, so memory is very, very poor. Fine, no issue. We can have again a discussion about that, how we can generate the pseudo-random numbers for a given length. Okay, what I said here is the information will be also in the form of zeros and ones, right? This spreading code is also in the form of zeros and ones, but the length of the pseudo-noise code will be much greater than the length of the information sequence. So by multiplying these two, I can say I am able to spread this information bearing signal over a wide bandwidth. So that is what is shown here. I don't know how many of you are able to visualize this. So this is what the information signal. I said that will be multiplied with the pseudo random code. That multiplication yields, okay, spreading of this information signal over a wide bandwidth. Okay, so and this pseudo random code is independent of the information bearing signal. Okay, so this is how it is done. In a layman language, what we can understand is that, okay, so spreading of the message signal spectrum is done by using a spreading code. The spreading codes are known as what? Pseudo noise codes. Okay, and as I said, this pseudo noise code is independent of the message signal. Fine. I will show with waveform also. Then I think you will be able to visualize how this information signal has been spreaded by using this pseudo noise code. Okay, so before that, just let me say the block diagram of this spread spectrum digital communication system. So I think I expect answers at least for this. What are the different blocks involved in digital communication system? Yes, any one of you can say. Yeah, be faster. First, you don't have to say about digital communication system. At least communication, you people can say, na? Whether it is digital or analog, that is secondary. If I say I need to have a communication, to say communication system, what are the main blocks I need? Or we talk about that? Yes, be fast.
Transmitter, receiver.
Very good. One is the transmitter. Yeah.
Coding and decoding. Encoding.
Okay,
Encoder.
coding and decoding. Fine. Then?
Modulator and demodulator.
Yeah, modulator, demodulator. Fine. Then?
Channel, receiver.
Yeah, so channel, receiver, right? So broadly we say transmitter, channel, then receiver. So these are the three main blocks of any given communication system, right? In transmitter, again we say different blocks. That is, first what we do, the information source, what we say, right? So it will be analog in nature, that will be converted into digital one by using analog to digital converter. Then we all know that will have so much of redundant information, right? So that can be avoided by using source coding. Okay, by using source coding. So you might have studied different types of source coding techniques, and the purpose of the source coding is to what? To represent the information as efficiently as possible, so that we can reduce the requirement of the bandwidth. Okay, so that is what is done at the first level, source encoding we say. Okay, after source encoding, then there will be modulators, right? So, and you have studied what are the different types of modulators which we can use in analog and as well as digital communication. So that is what is shown here in the block diagram. Okay, hope you are able to understand this, right? So I am going to say what is added with respect to this spread spectrum digital communication system. Okay, so information sequences, we get zeros and ones. That will be first passed through channel encoder. Yeah, before that there will be a source encoder, right? Then channel encoder. See, the purpose of channel encoder is what? What I said, in source encoding we remove the redundant information bits, right? But in channel encoding, we can add some amount of bits in a controlled manner, so that we will be able to achieve the reliable communication. Okay, that is the purpose of channel encoding. Hope is it possible to say what are the different types of source encoding and channel encoding techniques which you have studied so far? Yes, my dear students, you have studied one semester. In one subject, you have studied all those techniques. Is it possible to just mention the names of source encoding techniques and channel encoding and decoding techniques? Hello? Hello? I am asking you people to say what are the source encoding techniques and what are the channel encoding techniques. What is this you have studied just in the previous semester? Is it not possible to say the names at least? Yes, be fast, no? Not getting any response. Source encoding, then channel encoding.
Huffman,
Yes, Huffman coding. Very good. Then,
channel.
yeah, what about others? Why others are not speaking? Only Shreyas, Kanda, and few students are respond. What about others? Others don't remember anything? Yes, I'm asking others to respond. If you don't respond,
So modulation technique.
pardon? Yeah, two people have started communicating simultaneously. I could not hear anything. Is it possible to repeat?
So modulation techniques.
Yeah, I will come to that modulator. I was asking about source encoding and channel encoding techniques. Okay, Karuna, you were saying about modulation techniques. Now, what are the different modulation techniques? Is it possible to say in digital communication?
Amplitude modulation, frequency modulation, pulse code modulation.
Yeah, that is amplitude modulation, frequency modulation is in analog or digital?
Analog, sir.
Analog. Okay, what about digital?
Pulse code modulation, PCM.
Okay, then. Yes, we have discussed it in the last module in this semester only about all digital modulation techniques. I expect at least proper answer for this different
So phase shift,
digital modulation techniques. Yes.
FSK and
Yeah. Yeah. Mention no only one you are mentioning FSK.
BPSK, QPSK. So.
Yeah, BPSK, QPSK, FSK, that is BFSK, right? Then MRA FSK, then QAM, MRA QAM, right? So they're all different modulation techniques which are used in digital communication, which you have discussed. Fine. Okay. So what I was telling is at the transmitter side, I said the information sequence will be first passed through source encoding to remove the redundant information so that we can save the bandwidth. Then it will be passed through the channel encoders. So there we are going to add some amount of control amount of bits so that it is possible to achieve the reliable communication. So here reliable communication is what to minimize the means to maximize the SNR. Okay, ratio. Even in interference, we should be able to communicate. That is what done is here. And the, as I said, the modulators type of modulation techniques preferred in spread spectrum communication is BPSK and as well as FSK. Okay, so these are the two widely used modulation techniques in spread spectrum digital communication system. Even other modulation techniques can also be used, but we are going to discuss about these two things. Okay, then channel, fine, it may be wide or wireless. So then at the receiver side, there will be demodulators, right? Then channel decoder, then output of channel decoder will be given to source decoder, then we'll get back the output data. Okay, so only what is added here is in case of spread spectrum communication, and in what way it is different from normal digital communication system is, here we are going to use the pseudo noise sequence generator. Hope you are able to see the block of that pseudo noise sequence generator, which is given at the modulator and as well as demodulator block. Yes, my dear students, are you able to see that block, pseudo noise sequence generator?
Yes, sir.
Yeah. So this is what the difference is when compared to normal digital communication system. So what we do here is we are spreading the information sequence by using this pseudo noise sequence generator, and then we do the modulation. Okay, as I said, either BPSK or FSK. No? So accordingly, that spreaded sequence will be either phase modulated or frequency modulated. Okay, and even at the receiver side, we are using the pseudo noise sequence generator, I said, right? And these two should be time synchronized. Okay, the pseudo noise sequence generator, whatever we use at the receiver, should be in synchronism with the pseudo noise sequence generator which we use at the transmitter side. And even the value of the pseudo noise sequence should be of the same type. Then only they will be able to despread the signal and extract the original information. Okay, for other users it will be a noise. Hope you are understanding what I am saying. Whatever the pseudo noise code I use at the transmitter side, the same pseudo noise code has to be used at the receiver side. Okay, only if those two are synchronized in time. Okay, and only that intended user will be able to despread the information and get back the original data. Okay, this is how the spread spectrum communication works. Okay, so in normal digital communication, we were not having this pseudo noise sequence generators at the transmitter side and as well as at the receiver side. So here, by using this pseudo noise sequence generator, what I said, we are going to spread the information over a wide bandwidth. So by doing that, after that only we do the modulation. Okay, either BPSK or FSK. Then at the receiver side, the reverse process will be done. Okay, again we do the despreading, then demodulation, then channel decoder will get the output back, right? So what I said is we are using two identical pseudo random sequence generators, one at the modulator side and another one is at the receiver side. Okay, that is at the demodulator. Okay, the purpose of these two pseudo noise sequence generator is to produce the pseudo noise binary valued sequence, and that pseudo noise binary valued sequence is used to spread the information signal, that is the transmitted signal at the modulator, and to despread the received signal at the demodulator. Okay, so here one requirement is what is that the time synchronization of the pseudo noise sequence which is generated at the receiver with a PN sequence, right, which is contained in the received signal, is required, okay, to be properly, means it should be in synchronism with the pseudo noise sequence which is transmitted to the transmitter side, should be in synchronism. Then only it is possible to properly despread the received spread spectrum signal. Okay, if there is no synchronization, then it fails. So first synchronization will be done and then the information will be transmitted by doing the modulation. That is what is happening here. Okay. Yeah. As I already said, we use two different types of modulation techniques preferred in spread spectrum communication. One is, I said, phase shift keying, and another one is frequency shift keying, right? So where do we use or when do we use PSK is wherever the applications where phase coherence between transmitted signal and the received signal can be maintained, okay, over the time interval that spans several symbol intervals. So in such cases, we prefer phase shift keying, and we prefer frequency shift keying in applications where phase coherence of the carrier cannot be maintained, okay, due to time variations in the transmission characteristics of the communication channel. Okay, in such cases, we prefer frequency shift keying. To just to give an example, what I can say is the communication link between two high-speed aircraft. Okay, communications link between two high-speed aircraft or between the high-speed aircraft and the ground-based terminal. So in such cases, we prefer FSK rather than PSK. Okay, so based on these two types of modulation techniques which we use in spread spectrum, we classify spread spectrum signal as what? Direct sequence spread spectrum, and another one is frequency hopped spread spectrum. Okay, in case of direct sequence spread spectrum, the pseudo-noise sequence which is generated in the modulator is used in conjunction with the PSK modulation, okay, to shift the phase of the PSK signal pseudo-randomly. Okay, so that is why that is known as the direct sequence spread spectrum. Okay, so direct sequence spread spectrum means the type of modulation used is BPSK, right? So whatever the pseudo-noise sequence which we generated the modulator, right, that is used in conjunction with the PSK modulation to shift the phase of the PSK signal pseudo-randomly. And another one I said it is a frequency hopped spread spectrum signal. Here, the pseudo-noise sequence which is generated at the modulator is used in conjunction with the frequency shift keying modulation. Okay, so the pseudo-noise sequence is used to select the frequency of the transmitted signal pseudo-randomly. That is why it is called a frequency hop spread spectrum signal. Okay. So based on the type of modulation what we use, we classify the spread spectrum signal into two types. I said one is direct sequence spread spectrum. Second one is frequency hopped spread spectrum. Okay. So let us try to understand with the mathematical equations how we can say how do we spread the information signal, okay, over a wide bandwidth, and then we modulate and transmit, and we say it provides secure communication. Okay. Okay. So to understand that, first we need to express how do we represent the information bearing baseband signal. Okay. So the information bearing baseband signal means what? The message signal. Okay, how do we express that mathematically is, so we express that mathematically as b of t is equal to summation n is equal to minus infinity to infinity a suffix n, okay, gt of t minus n into tb, where the value of this an, so this is the amplitude level, okay, an is the amplitude level, it may be plus or minus 1. Okay, so the value of the amplitude level we take either plus or minus 1. So over the what value? This n value of n can range from minus infinity to plus infinity. Means what? You should be able to visualize a rectangular pulse. Okay, rectangular pulse having an amplitude of plus 1 volt and minus 1 volt. Okay, so this an, as I said, it indicates what? Amplitude of the pulse. So its value is what? Either plus 1 or minus 1. Means it is polar NRZ waveform, what I can say. Okay. Then this is GT of T. Okay. G capital T of T is what? Is a rectangular pulse. Okay. Of duration TB. So TB is the bit duration, what we say. And it is shifted. Means see GT of T minus N into TB we say, where the value of n can vary from minus infinity to plus infinity. Okay, say for example, let me say 5 bits are there. Okay, 5 bits are there. You can think of 0, 1, 0, 1, 0 like that. Okay, so 0, 1, 0, 1, 0 is said, right? So here, if I say polar NRZ, okay, if I say I represent that binary information by using polar NRZ encoding. So how do I represent 0? 0 will be represented by what? Yes. How do I represent 0 in case of polar NRZ? You are studied this in this semester only, in the first module. I have given one example that, let me consider 5 bits, right? What I said, it is 0, 1, 0, 1, 0. I am asking, how do we represent this 0, 1, 0, 1, 0 by using polar NRZ? 0 is represented by what? Hello? Yes, my dear students, please respond. Polar NRZ I am asking. How do we represent 0? How do we represent 1?
Sir, 0 is by a negative pulse of
0 is represented by a negative pulse, maybe having an amplitude of say minus 1 volt. Right. What about 1?
positive pulse with plus A volts.
1 will be represented by a positive pulse having an amplitude of plus 1 volt. So that is what I am saying here. Means first, and I said it is 5 bits, right? 5 bits. Hope you got this point. Amplitude. Why I say summation? Right, summation of n is equal to minus infinity to infinity an gt of t minus n into db. Here, what is the value of n you are going to take if for this 5 bit? So for 5 bit, the value of n will be 5, right? If I say the number of bits is 5, so you are going to take 5. N is equal to 5, right? So means each bit duration will be what? 1 over 5, right? 1 over 5 will be the each bit duration. So the shifted version of that means I represent each bit by rectangular pulse. I multiply that with the amplitude of the signal, right? So that is how I represent mathematically the entire the information sequence like this. Hope you got this point. How do I represent mathematically the information bearing signal? I don't know how many of you could visualize that. I said an is the what? Amplitude of the pulse. Okay, gt of t is the pulse, right? I said how do I represent by using polar NRZ waveform? I represent 0 by a negative pulse and 1 by a positive pulse. So that is indicated by this an. Okay, and this gt of t minus n into tb, I said what? It is a rectangular pulse. Why I am shifting this and represent multiplying that? I said one code word. If I say one code word, I have taken here an example of 5 bits, right? So you will be able to say what is the bit duration out of those 5 bits. So if I say it is 5 TB, then each bit duration will be 1/5 of that, right? 1 by 5, and next bit will be. Hope you are getting that point. Able to visualize that rectangular pulses. Negative pulse, positive pulse, negative pulse, positive pulse, the negative pulse. You can just think that with respect to my example 0, 1, 0, 1, and 0. Okay. So similarly, as I said, this pseudonoise sequence, okay, PN signal from the pseudonoise sequence generator can be represented like this C of t. We represent it as C of t. So it is also a rectangular pulse only. Okay, so that is why it is written in the same fashion. Summation n is equal to minus into infinity Cn. Instead of an, we write here Cn, P of t minus n into Tc. Okay, since it is pseudonoise sequence, in the same way I have written. Okay, again here Cn value can be either plus or minus 1. Okay, again P of t will be a rectangular pulse only. Okay, so Cn represents the binary pseudonoise sequence of plus or minus 1s, right? And P of t, I said it is a rectangular pulse of duration Tc. Is that fine? So expressing mathematically information sequence and as well as the pseudonoise sequence. Yes, my dear students, could you visualize this?
Yes, sir.
Yeah. Okay. So after that, what we do is we multiply that, right? Means V of t and C of t. Okay. So that is what, when I multiply, it is nothing but a what? Product modulator, right? Information signal is multiplied with the pseudonoise sequence. Okay. V of t into C of t we get. So when we multiply, what we get? We get a DSBC signal. Right. This we know very well with respect to your analog communication only. We said M of t, C of t. If I multiply that, what we get? We get a DSBC signal. So that is what is written here. Okay, this V of t into C of t will be equal to what? It is plus or minus 1 magnitude, right? What we say for any value of t. Okay, so this AC cosine of 2 pi of Ct is the carrier. Okay, so V of t is your information signal, C of t is a pseudonoise sequence, right? So those two multiplied with the carrier. Okay, so I can express, means this as a DSBC signal, what I said, I can express this in another form as like this: AC cosine of 2 pi of Ct plus theta of t. Okay, this is how I express in a standard form of modulated signal. Okay, AC cosine of 2 pi of Ct plus theta of t. So here, in case of BPSK, so it depends on the value of theta of t, right? When theta of t is 0, right? When theta of t is 0, we send some information signal, either 1 or 0. Okay, then when theta of t is pi, we send another information signal, that is 1. Okay, it may be vice versa also, right? That is what we say, it is BPSK, right? Binary phase shift key. We send 0 with one phase and 1 with another phase. Okay. Yeah, just to get an idea, let me say about this information signal. What I said, no, data signal is nothing but your information signal. Here I have taken only 2 bits. One is 1 and another is 0. Okay, so the first bit is 1 and second bit is 0. Hope it is clear. And its magnitude I have written as +1 and -1. So 1 I represent with positive pulse and 0 I represented with negative pulse, having a magnitude of -1. Okay, and I say this is my bit duration. Okay, which is denoted as TB. Hope is it clear? My information signal is what? 1 and 0. Only 2 bits I have taken. The bit duration I am writing it as TB. Okay, I represented 1 by a positive pulse having a magnitude of +1 and 0 by a negative pulse having a magnitude of -1. Okay, so next is pseudonoise signal. That is what? C of t, right? So here my pseudonoise signal length is 7 bits I have taken. Okay, 7 bits I have taken. What is the 7 bit is 0, 0, 1, triple 1, then 0, 1. Okay, so 00, 111, 0, 1. So I represented that also by using this polar NRZ format only. So 0, 0 I represented with negative pulse, and 3 ones I represented with positive pulse, then 0 by negative pulse, 1 with a positive pulse. And that has been repeated, okay, for the next bit also. Okay, so this TB is equal to N into TC, I can say. Okay, means this 1 bit, okay, is multiplied with this 7 bits of pseudonoise signal. Hope you're understanding what I'm saying. Yes, my dear students, are you able to understand what I'm saying? Hello?
Yes, sir.
Yeah, what I said here is I have taken 2 information bits. One is what? First bit is 1, the second bit is 0. Okay, I said how I represented that 1 and 0. 1 by a positive pulse and 0 by a negative pulse, right? And then this is my pseudonoise signal. Okay, what is the length of the pseudonoise signal? It is 7 bits. So I have taken 7 bits as my pseudonoise sequence length. What is the 7 bits I have taken here? 00, 111, 01. So I represented that also by using polar NRZ format. So here first 2 bits are there, 0, 0. I represent by a negative pulse. The next 3 ones are there, that I represented by a positive pulse. And then again next 0 is there, I represent that by negative pulse. Then next 1 is there, I represent that by a positive pulse. Again, that will be repeated for the next bit also. That sequence of n is equal to 7, that is the pseudonomous sequence length. I said n 7 bits now. That is repeated for next bit also. Okay, that is why it is written again 00, 111, 01. That is for information bit 0. Okay, so what I do, I need to multiply these two, right? So when I multiply P of t and C of t, what I get? See here, plus 1 is there, plus 1 is there. Okay, here minus 1, minus 1. So plus 1 into minus 1, what I get? Minus 1 only, right? That is what is written, minus 1. Next also plus 1 and minus 1. So minus 1 I get. So that is what is written, minus 1. Then for next 3 bits, so here it is plus 1, right? Pseudonomous sequence C of t is plus 1. And my information bit is also plus 1 only, right? So that is why I get plus 1 only. Then next is what? Minus 1 is there. So here plus 1 is there. So plus 1, minus 1. I will get minus 1. Next is what? Here plus 1 is there. Here plus 1 is there. So plus 1 into plus 1, it will be plus 1. Okay. So next, what is there for bit 0? Here, here minus 1. Here also minus 1. So minus 1, minus 1, I will get plus 1. So that is why it is continued with plus 1. Next bit is what? Minus 1. Here also minus 1. So minus into minus, it becomes plus 1. So plus 1 is there. Right. Then next is what? Here it is minus 1 is there, but my pseudonomous sequence length is what? Plus 1. So minus 1 plus 1, it will be minus more bits, it will be minus 1 only. Okay, next is what? Here minus 1 is there. Here also it is minus 1, right? So minus into minus, it becomes plus 1. The next last bit is what? Here minus 1 is there. Here it is plus 1. So minus 1 plus 1, it will be minus 1. Okay, so this is how my spreaded signal is. Okay, so I spreaded this information bit 1 over the 7 bits of pseudonomous sequence. Yes, my dear students, is this point is clear? Very simple, just multiplication only. Yes, is it clear?
Yes, sir.
Hello?
Yes, sir.
Yeah.
Yes.
Yes,
Yeah,
sir.
yeah. The here means the information bit, as I said, it is a low frequency signal, right? That is why I have taken, this is what my bit duration. Okay, means bit duration 1 is this much time is taking, right? But it is a high frequency signal, the pseudonomous signal. Okay, that is why the bit duration of this pseudonomous signal will be means time is less, right? So in 1 bit duration, I have 7 bits of pseudonomous signal. So just I'm multiplying those two, I get the spreaded signal. So this spreaded signal will be phase modulated, okay, or frequency modulated, depending upon what I use, whether direct sequence or frequency hop. So if it is phase modulated, then I send this 2 zeros by 180 degree and 3 ones by 0 degree, like that. Okay, so that is what is done here. So same thing I am expressing in a different way, that is in the frequency domain, what I said here. So I have taken the rectangular pulse, okay, that is my spectrum of the information signal, okay, and this is the spectrum of the pseudonoise signal. So the spectrum of the pseudonoise signal is wider than the spectrum of the message signal, right? So I multiply in time domain. So multiplication in time domain leads to what in frequency domain? It will be Fourier transform of their convolution in the frequency domain, right? Even vice versa also I can say, means if 2 signals are convolved in time domain, it will be equal to what? The Fourier multiplication of their Fourier transform in the frequency domain. I hope you all know that very well, the convolution theorem, right? So here I have taken the spectrum of the message signal, and this is my spectrum of the pseudonoise signal, and This is the spectrum of my split spectrum signal. Okay, so two rectangular pulses of different widths. If you convolve it, what you get? You will get a whatever waveform it is. It is a trapezoidal waveform, right? Yes or no? Hello? See, this is my one rectangular pulse. Okay, this is another rectangular pulse. But their widths are different, right? If I convolve these two, I get a trapezoidal waveform, I said. Okay, you will just take one example of taking some value of this and value of this also. You try it. So you may take 1 hour time to do that. Okay, convolution of two signals. Two rectangular pulses of different width, you will get the trapezoidal waveform. So that is what shown here. Okay, so any doubts so far? So here I told in terms of time domain, okay, by taking what is the information bit duration and what is the pseudo noise sequence length and what is the duration. If you multiply, how do you get the spreaded signal? Okay, this is told in terms of frequency domain. Yes, my dear students, do you have any questions or shall I proceed? Okay, so as I said, that this information will be at what rate? It will be R bits per second, right? With the available channel bandwidth, we say it is W hertz. Okay, so that is the available channel bandwidth. Then we know the reciprocal of this R will give the bit rate. That is a TB, bit duration, right? That is bit rate means RB is equal to 1 by TB, we say, right? So bit rate is equal to 1 over the bit duration. So vice versa also we can say. So TB is equal to 1 by R. So that will define the pulse duration. Okay. Then we say pseudo noise code will be transmitted at a rate of what? W times per second. So reciprocal of that will give you the chip duration. So T suffix C. We call this as the chip duration of the pseudo noise pulse. That we call it as a chip. That is why it is denoted as T suffix C. Okay. So T suffix C is the what? Chip interval we say. Okay, so what we can think is, so the duration of the pseudo noise signal is written as what? TC, I said, right? So this is 1 TC, 2 TC, like that. 7 TCs are there here. Okay, 7 TCs because I have 7 bits. Right? That is multiplied with 1 TB. That will give you the duration of your spreaded signal. Yeah. Yes, I was telling about this now. When theta of t is equal to 0, means with respect to this equation, I can express the output of the modulator as what? AC cosine of 2 pi of ct plus theta of t, right? So this theta of t will be 0 when that v of t into c of t is equal to 1, and that theta of t will be equal to pi when that v of t c of t is minus 1. So when v of t c of t will be plus 1, when both information bit and the pseudo noise sequence both are positive or both are negative, then only their product will be positive, right? So if any one of them is of opposite polarity, then I get that product as minus 1. In that case, I send that information with a phase of 180 degree, right? That is why I said we are transmitting BPSK signal. So I told, I think about this already, the rectangular pulse, we call that as a chip, and its duration as TC. We call that as a chip interval. Okay, this is about the pseudo noise sequence pulse duration. So 1 by TC, we call that as a chip rate. Okay, 1 by TC is the what? Chip rate. That corresponds to bandwidth of the transmitted signal. Means what I mean to say, W is equal to 1 by TC, I can say. Okay, so the ratio of this bit interval, that is TB. TB I said, that is the duration of the information bit, right? The ratio of this bit interval to the chip interval. So that is TB by TC will be a integer, okay? And we denote that as the L suffix C, that is the length of the chip sequence, what we say. So LC is equal to TB by TC, we say, where LC is the what? Number of chips of the pseudo-noise code sequence per information bit. Okay, so per information bit, how many pseudo-noise sequence bits we use? In the example, what I have considered, I have used 7 pseudo-noise chips, what I can say, or bits per information bit. Okay. Yes, is this clear? LC is the what I said, number of chips of the pseudo-noise code sequence per information bit. And this also, this LC represents the number of possible 180-degree phase transitions in the transmitted signal during the bit interval dB. So that you understand with respect to this, right? We said if it is minus, what we said with 180-degree. If it is plus, the product. B of t, C of t, if it is plus, we send with 0-degree phase shift. Right, so the number of 180-degree phase transitions it will indicate. Yeah. So hope you understood what is L suffix C. L suffix C is the what? The number of chips of the pseudo-noise code sequence per information bit. Okay, and I said this L suffix C also represents the number of possible 180-degree phase transitions in the transmitted signal during the bit interval TB. Okay, so this relation is very important, TB by TC. Okay, so simple problems they will give. They will give the bit duration, they will give the chip duration, they will ask you to calculate other parameters. Okay, means you know 1 by TC, right? If they give chip interval, you can calculate what is the bandwidth. Okay, W is equal to 1 by TC, we can say. Fine, so this is all about the transmission side. So similarly, the reception side. So what we need to do as a first step at the receiver side, we need to de-spread the signal, right? So at the transmitter side, we spread the information signal and then modulate, then transmit over the channel, right? So first step at the receiver side is to what? To de-spread the signal. So what we do here, so R of t is the received signal we say, right? That need to be multiplied by the pseudo-noise sequence. So this pseudo-noise sequence should be the same as that of the pseudo-noise sequence which is used at the transmitter side. Then by doing so, okay, by multiplying the received signal by the same pseudo-noise sequence, we are going to do the de-spreading of the signal. After de-spreading, right? So this first step is the de-spreading. Then we multiply that with the cosine wave. Okay, gt of t is a pulse and carrier, this one. Means it is a carrier signal, right? Gt of t into cos of 2 pi of ct. See here, multiplier followed by an integrator is there. Means it is a correlator. Okay, so it is a correlator block. You all know what is the function of correlator. What it will do, it will get the sample vector, right? So that is what is done here. Then whatever the sample we take, it is the output of this correlator, that will be synchronized with the clock signal. Then it will be given to the decoder to estimate what is the transmitted binary sequence. So this is how the direct sequence spectrum demodulator works. The first step is what? We need to de-spread the signal. How do we do that de-spreading? By multiplying the received signal with the same pseudo-noise sequence, which is used at the transmitter side. After that, we have a correlator, that is multiplier followed by an integrator. So that will generate the sample, right? So this sampler will be what? Another input given to the sampler is clock signal, right? So this is need to be synchronization. Okay, that the clock has to be estimated so that exactly at that particular sample, time interval, what is the value of that sample. Then it will be going to the decoder. You know what is the decoder will have. It may be ML decoder, it may be in other things. Okay, so that is all for the estimation. So just to say, how do we at the receiver side, right? So the received signal will be multiplied by, again, that pseudo-noise sequence. That is why we know what is U of t. That is the transmitted signal, right? So AC V of t. Again, we multiply with C of t, right? That is why written as C square of t into cos 2 pi FCT. Okay, and we know, so U of t is this. Right, U of t is this AC, V of t, C of t, cos 2 pi FCT. Now, this is multiplied by C of t. If I do that, what I get? I get this one, AC, V of t, C square of t into cosine of 2 pi FCT. So the value of C square of t will be equal to 1 for all values of t. So that you can check. Whatever the pseudo-noise sequence I have taken, you multiply that C of t into C of t. So that is C square of t, its value will be equal to 1. So what is the resulting signal I get? AC V of t cos 2 pi FCT. So this signal will be occupying the bandwidth of Hz. So which is the bandwidth of the what? Information bearing signal. So based on this, we conclude that the information signal has been extracted at the receiver side. So this is how this spread spectrum communication works. Okay. So let me stop with this.